Hey everyone! Ever stopped and wondered what's really going on inside your computer? I mean, deep down at its very core. Today, we're going to peel back that curtain and look at the secret language of the CPU itself. These are the tiny, fundamental instructions that make literally everything happen. From your mouse moving across the screen to you watching this right now. Let's dive in.
So yeah, how does a computer actually do anything? It's a great question, right? Because it doesn't understand high-level commands like open a file or launch that game. Nope. At its heart, a computer is this incredibly powerful but super literal machine. It only understands a very small handful of commands. Everything, and I mean everything it does, is just a combination of these simple little instructions happening faster than we can even imagine. All right, so here's our game plan. We're going to build this up from the ground floor, just like a real program does. We'll start with the processor's basic vocabulary. Then we'll see how it moves data around, how it does some math, how it makes decisions, and finally, how it ties all of that together. It's going to be fun.
Okay, let's start at the very beginning. Let's talk about the processor's vocabulary.
Every single processor speaks its own unique native language, and that language is called an instruction set. Now here's the wild part. It's not like English with thousands of words. An instruction set might only have 100 or so commands. But with just that small vocabulary, it can pull off any calculation you can dream of. It's the ultimate example of doing more with less.
Now, before we get to the actual instructions, we need to understand where all this work happens. I want you to picture the CPU as a workshop. Inside this workshop, you've got a couple of super fast workbenches. These are called registers, and they're for whatever you're working on right now. Then, outside the workshop, there's this massive warehouse. That's your memory, your RAM. It's where you store all your tools and materials, your programs and your data, until you need to bring them into the workshop.
Which brings us to our next section, moving and storing data. Because really, the first and most common job for any processor is just moving things around. Getting data from that big warehouse to a workbench, or maybe shuffling things from one workbench to another. This is the absolute foundation for everything that comes next.
So how does it do that? Well, there's an instruction called MOV, which is short for move. It's pretty straightforward. It just copies data from one workbench, or register, to another. So MOV A just takes whatever's in register B and copies it over to register A. Simple. But what if you need a specific number that isn't already on a workbench? That's where MVI, or move immediate, comes in. It's like telling the CPU, hey, just take the number 5 and stick it directly onto workbench B. You're loading a specific value right in there.
Now this is where it gets really interesting, the traffic between the workshop and the warehouse. There's a special, really important workbench called the Accumulator. You can think of it as your main workbench. The LDA instruction, for load accumulator, is like sending a runner out to a specific shelf in the memory warehouse, telling them to grab whatever's there and bring it back to that main workbench. And then you have STA, or store accumulator, which does the exact opposite. It takes whatever is on your main workbench and sends it back out to be stored on a specific shelf in the warehouse.
But wait a minute. To find anything in that giant warehouse, you need an address, right? A shelf number. That's where the LXI instruction comes in. You can think of this as the instruction that gives the CPU a map. It loads a specific memory address into a pair of registers. Without this map, the CPU would be totally lost, just wandering around the warehouse. LXI points it exactly where it needs to go for the next pickup or drop-off.
Okay, cool. So we can move data around. That's awesome. But it's really just logistics, right? We're just shuffling boxes. How does a computer actually do anything useful with that data? Well, now we get to the good stuff.
This is where the real work begins. You've got these super simple instructions, like add and sub. The CPU grabs a value from one of its workbenches, adds it to or subtracts it from whatever's on that main workbench, the accumulator. And guess where the result goes? Right back onto the accumulator. That main workbench is truly the center of all the action.
And you know, sometimes you don't need to do a big, complex calculation. You just need to add one or subtract one, like when you're counting. For that, you've got these handy little instructions, INR for increment and DCR for decrement. They're super efficient ways to just bump a value up or down by 1. Perfect for things like counting down a timer or running through a loop a certain number of times.
All right, so we can move data, and we can do math on it. That's great. But the real leap, the thing that makes a computer feel, well, smart, is its ability to make decisions. This is where we get to the foundation of what you might call computer thinking.
So here's the secret sauce. After every single calculation, the CPU leaves itself little sticky notes. Seriously, they're called flags. These are special little bits that record important stuff about the result. Like, hey, was the result of that last subtraction 0? The 0 flag will tell you. Or did that addition problem create a number that was too big to fit? The carry flag will tell you. These flags are basically the CPU's short-term memory of what just happened.
And there's this one instruction that just shows how brilliant this system is. It's called CMP, for compare. What it does is it subtracts one number from another, but, and get this, it throws the answer away. It doesn't care about the result of the subtraction at all. Its only job, its entire purpose, is to set those sticky note flags. Is the value in the accumulator bigger, smaller, or the same as the other value? The flags will tell you.
So let's think about that. What happens if we use CMP to compare two numbers that are exactly the same? Say we compare 5 with 5. What's the result of 5 minus 5? And what does that mean for our little sticky notes?
The answer is 0, of course. So that little sticky note, the 0 flag, gets flipped on. The CPU now has a record, a little 1 sitting in the 0 flag spot that tells it those two numbers were identical. And it figured this out without actually changing any of its data. This simple fact, well, it changes everything.
And here's why. Because now that the CPU can check its little sticky notes, it can change what it does next. It's no longer just blindly following a recipe, one step after another. It can now make a choice. This is how we get to control the program's flow. This is the big payoff, right here. There's another instruction, JZ, which means jump if 0. The CPU looks at that 0 flag sticky note. If it's on, if it's set to 1, the CPU doesn't just go to the next instruction in the list. Nope. It jumps to a completely different part of the program. This is your if statement. This is the fundamental building block of all logic in all software everywhere. It's that simple and that powerful.
And of course, there are a bunch of other control instructions. You've got JMP, which is just an unconditional jump, like don't ask questions, just go over here now. You have JC, jump if carry, which is super useful for checking if a math problem overflowed, and then you have in and out, which are how the CPU actually talks to the outside world, how it gets input from your mouse or sends output to your monitor.
What's really neat is how it handles interruptions. Think about it. The CPU is busy running a program, and then you click your mouse. That click is an interrupt, an urgent message saying, hey, stop what you're doing and deal with me. To manage all these potential distractions, the CPU has special instructions that act like a control panel. It can use these to decide which interrupts to listen for and which to ignore, basically putting some tasks on Do Not Disturb so it can focus on what's most critical.
Okay, let's pull back for a second and look at the big picture. We've gone through a lot of little details, but what's amazing is how a handful of really simple ideas come together to create all the complexity we see in our software.
It really boils down to these 4 pillars. First, you have data transfer, just moving information between the workbenches and the warehouse. Then, arithmetic, doing the math and changing that data. Third, logical operations, comparing things and setting those critical sticky note flags. And finally, branching, using those flags to make decisions and change the path the program takes. That's it. That's the whole game. Every single thing your computer does is just some combination of those 4 things happening millions of times a second.
You know, when you think about it, every app on your phone, every complex video game, every piece of software that runs our world, it's all built from these ridiculously simple rules: moving, calculating, comparing, and jumping. It's a pretty amazing reminder that the most sophisticated systems are often just simple building blocks, stacked in clever ways. So what could you build with them? Thanks for watching.